Konstanz here to give a presentation. He is a formal faculty candidate for the School of Computing and SCIIInstitute Visualization open position. He'll be giving two talks, one today, which is the a general overview talk about his work, and then on Wednesday at noon, same place, same time, and with pizza, he will be giving a Viz Lunch talk, which will be a more technical visualization talk. So please come back for Wednesday after you see his talk here. So we'll let you start. Nice, welcome.
Thanks, Chris. I prefer to stay here. So hi everyone. I'm Enrico Bertini, and as Chris said, I come from the University of Konstanz in Germany. And before going there, I'm originally Italian from Rome, and I have my master's degree and PhD degree from the University of Rome, La Sapienza, and then I moved for some time to Switzerland in a nice city called Fribourg, where I did a whole bunch of applied information visualization there. And then I moved to Konstanz in the group of Professor Daniel Keim, when together we do a lot of different kinds of projects, and I'm mainly working into high-dimensional data analysis and integration of automatic and interactive techniques, and some evaluation for information visualization. So my talk today is about visual analytics, building the science of analytical reasoning facilitated by visual interfaces together. And I will start by saying that I think it's not big news for you if I say that we live in the era of data. So actually we are surrounded by data, and what is really remarkable is that we are capturing almost every aspect of our life or human processes right now. So we have things like transactions, Twitter feeds, large volume scientific data, logistics, body sensors, emails. We have a whole bunch of stuff produced every day at a very, very high rate. There is a very interesting report that I read recently from the McKinsey Global Institute, which is a research branch of McKinsey and companies, called Big Data, the Next Frontier for Innovation, Competition and Productivity. I think it's really interesting. They analyze many different markets and how big data and data analysis in general can help boost these markets. And there are all sorts of predictions, which of course you can believe or not, but I think it's interesting to see how they predict how this field can help actually boosting the economy and also doing great things for society in general. There are a couple of things that I extracted from the report. Of course, some big numbers, which maybe for you are not too surprising, like 235 terabytes data collected by the US Library of Congress by April 2011. 15 out of 17 sectors in the United States have more data stored per company than the US Library of Congress. I think this one is really surprising. I was really surprised. Another thing that I think is interesting for American universities in general, which is the fact that they project for 2018, a projected demand for deep analytical talent, which is much, much bigger than the projected supply there. So there is a sort of between 50 and 60% gap of people that universities will have to generate, or the market in some way will have to generate to cover this deep analytical talent gap, which I think is interesting. What is really interesting from my point of view is not only that, of course, people can build thriving businesses out of this big data, is the fact that we can do good things with data. So for instance, we can help, I mean, some of you guys know it better than me, we can help doctors treating their patients, we can help people like biologists or biochemists to develop advanced drugs, or we can help financial analysts understand their data and maybe even prevent problems before they come. And we can even help policymakers understand what people need, what people want, and maybe create better policies. And this is actually already happening. There are people who are doing some kind of A/B split testing and giving one policy to a region, another policy to another region, and then comparing the results, which I think is really interesting. Of course, if this is remarkable, interesting, and really, really promising, from the one hand. From the other hand, we have to answer this important question: how do we help these people make sense of their data? And I think that an interesting aspect here, especially compared to, I mean, we have had data analysis for a very long time so far, but what has changed is not only the volume of this data, which is really, really impressive. On the other side, we have people that I call casual data analysts, which are people that all in a sudden, even if they are not trained to deal with such a complexity, they have to work with this complex data and extract complex information out of it. So I think it's our responsibility as computer scientists to provide them with the tools for thought that they need. I think this is a big challenge. So Richard Hemming said, the purpose of computing is insight, not numbers. And I think this is important. And visual analytics, the way I see it, is basically the science that tries to study how to derive insights out of big data. Visual analytics has been formally defined in the visual analytics agenda, illuminating the path, as the science of analytical reasoning facilitated by interactive visual interfaces. So the idea basically is to use visualization as a way to give a look to data, interact with the data, and understand their content. But I think it's not only a matter of visualization, it's a whole bunch of things. And this is the way visual analytics is somewhat different from visualization itself. Of course, visualization is a big part, but there are many other aspects in visual analytics. First of all, understanding the process of analytical reasoning. How do people reason with data? How do we create visual representation and interactions that help people deriving insights out of data? How do we manipulate, pre-process, and mine this data, especially when the kind of patterns that we want to extract are too complex or the data is too big? And also, how do we present and disseminate the results, and more in general, how do we support the sense-making process and the decision-making process? I don't want to talk too much about visualization or visual analytics without giving an example, so I will go here to my computer and give a little example that comes from my own work. I think I have first another slide. So this is a tool that we developed a couple of years ago that is called Flow Straits, and which is part of a project that I had funded from the Swiss National Science Foundation in collaboration with the United Nations. And the problem there was to understand how refugees go from one region to another region in the world and understand how this changes in time. And so what we tried to do at the beginning, we tried with very simple solutions that I'm going to show you, like this one. So flow maps are very common. Basically, a flow map is the idea of connecting the places where there is a flow going from one place to another, like here with a line, and then using the width of the line to represent how much, in this case, how many people are flowing from one region to another. But the problem we have here is that this data changes in time, and these researchers were more interested in seeing how this data changes in time. So one obvious way of doing that is to use animation, and then you can animate the results. And here you have, every step is one year, and of course you can see the development, how it changes. You can see big changes there. This is, for instance, Afghanistan. And you can see some changes there. So now the problem is that even if in a way it's cool, people like it, but it's not very effective. And in general, animation is not too effective for this kind of representations. So we tried to come up with some different solutions. Another problem here is that in order to represent the direction of these flows, we have to use some kind of artifacts. Like here we have color. Green is the place, is the starting point, and red is the end point. So we wanted to solve all these problems at the same time, so we came up with this little tool that is called Flow Straits, which basically tries to do something different. So it splits the origin of the flow and the destination of the flow into two different maps. And then in the middle there is a heat map that represents, every row represents one single flow in the map. and every column represents one single year. So now what happens is that we can interactively see for a selected region in the origin how flows go from this origin, how they develop in time and go to several destinations. I'm going to show you how it works in a moment. So here we have a slightly different data set. This is the data set called 8 data. So what is flowing is money. And this is money that countries or institutions lend to other countries to help them. Is it clear? Okay. Please, if you have any questions during my talk, feel free to stop me, okay? So, and here we have not only geographical regions, but also institutions. So sometimes we have from places to places or institutions to places, all the possible combinations. So let's see what we can do with this one. Let me see if I can make it bigger. So, okay, now what is nice is that since we have these, we can either start from the geography and see how certain places develop in time, or we can start from the heat map, see interesting patterns, and see where they happen. I will start with this one. So, for instance, we might be interested in seeing what are the biggest flows there and how they change in time, so I can resort the matrix. So one aspect of this work is that there are many different algorithms to resort this matrix, either by maximum value, maximum average value, maximum difference between one year and another, or maximum similarity between different years, and so on. So here we have the biggest flows, and now we want to see what kind of flows we have here. So we can zoom in. And what is interesting is that we notice that the biggest flows come from the International Monetary Fund. This is the IMF, means International Monetary Fund. So, and what is surprising here is that, as you can see, the International Monetary Fund, compared to other institutions or places, is pretty much intermittent. You see here? So it's very rare to see the International Monetary Fund having steady streams of money to another country. So one thing that I tried to do, I wanted to check, and I took every country here and trying to type in Google the name of the country, the year, and crisis. And almost every time there is a Wikipedia webpage coming up and say, yes, this is crisis in 1996 in this country, okay? So if you look at these points, it means pretty much one-to-one that every point here represents a crisis, and the International Monetary Fund gave money to them to help them for a very short time period, okay? So now we might be curious to see, okay, but what else does International Monetary Fund does? So I focus only on the International Monetary Fund, and as you can see, it's pretty much intermittent everywhere. It's always the same. Another thing we can do, so I forgot it. I wanted to go back to the other one. Clear. Another thing that you can see here is that if you want to give a look to the biggest streams, so the biggest streams at the beginning are from the International Monetary Fund, and the first country that has a very big stream is the United States here. And you might be curious to see what it is. So it's Iraq. I think it's not too surprising, by the way. And it's a long and steady stream starting from 2002 up to 2009. So maybe now we can focus on United States and see what countries United States actually helps. And the first one is Iraq. Then there is a pretty steady stream to bilateral unspecified, which is pretty strange. I don't know what it is. And then to Egypt, and then to Kuwait, which is pretty intermittent, starting in 88, then 91, and so on. Okay, I could continue forever. So I think this gives the impression that, of course, one problem here is that I'm not an expert in political science, but we are collaborating with people whose work is really to understand this data, and we are actually in the process of establishing a new project with them. These people behind this 8 data, they want to understand all sorts of patterns there. And again, they want to see how these patterns develop in time. So this is just to give you an example of the kind of work that I'm doing, or at least the applied work that I'm doing. So a good question is, when is visual analytics needed? I think that visual analytics is needed. We need 2 main ingredients to have a visual analytics problem. So the first one is that data is too large or complex. And this means that visualization doesn't scale. So in this example, the data set is still not too large, but in some cases, the data set is so large that there's no way to represent directly this information on the screen without some kind of pre-processing or compression. Okay? So the first point is visualization alone without some pre-processing or some analytical algorithms in these cases is not enough. On the other hand, we have that some problems need human judgment, and because they are hard or impossible to formalize. And in this case, using automatic methods is not sufficient, so we need to add a visualization component. So I think there are a whole set of problems that have this characteristic. Very big data set, complex patterns to find there, but at the same time you cannot solve the problem automatically. You need some interactive and visual component there. So instances of this, some examples could be understand interactions between molecules and proteins in an experiment. I've been myself working with biochemists, and of course, and it was clear for me by working with them that they needed this kind of tools. Understand how computer viruses changes. We have a very interesting project in Konstanz with Symantec, and they cannot really understand when they have new viruses. They have no algorithms that can actually really understand how these viruses behave. So the best way they are trying to solve this problem is to use visualization there. Or understand how distributed algorithms behave, or make sense of people and objects moving in space and time. For instance, we have another project with biologists ornithologists who are trying to understand how birds migrate from one region to another of the world. They have albatross and other kinds of animals. And there is a rule that I call the golden rule of visual analytics, which is don't use visual analytics if automatic solutions exist. So I totally believe in the fact that we shouldn't use visual analytics where you can solve the problem with a computer, because we don't want to involve humans in processing problems that can be solved automatically by computers. Okay? Of course, visual analytics come with a whole bunch of technical challenges. I will mention some of them. First of all, data complexity, which means many different things. Size and dimensionality, dynamics, which can come in forms of strings, uncertainty, and very, very exotic formats like text, images, video, audio, and so on. The second point is the integration of automatic and interactive techniques. How do we integrate in automatic and interactive techniques? How much automatism do we need there, and how much interaction do we need there? I think finding this split point there is an interesting research challenge. And then, of course, we need clever and effective visualization and interaction design to create smooth interactive visualizations of millions of data points, and to create optimal visualizations in terms of perception and cognition, which is another challenge. So this means that from the computer science point of view, visual analytics is pretty much multidisciplinary. We need people from all branches of computer science: databases, data mining, text analysis, natural language processing, image processing, computer graphics, human-computer interaction, perception. We need all this expertise here. Okay? I don't think that we can do visual analytics only with visualization people. We need help from everyone here. So this brings me to my own research. And here is what I call Enrico's research landscape, which is basically a short summary of all the things that I've been doing so far. So they can be categorized in three main islands. The first one is what I call visualization scalability. The second one is evaluation, and the third one is applications. So in visualization scalability, I've been focusing mainly on clutter reduction, which means basically when we have too many data points that we want to project, how do we reduce the size of this data set in a way that we don't lose interesting patterns there? And how do we measure that, actually? The second is, how do we deal with data sets with a very large number of dimensions? And the last one is, how do we deal with data that comes in form of strings? The second one is about evaluation, and I will have a large portion of my talk about evaluation, explaining why it is important. And I have been dealing with a whole bunch of domain experts. I have been doing this work on temporal flow maps with people from the United Nations, as I said, and political scientists. Then I have some work during my period in Switzerland. I've been working with people in network security and helping them, trying to help them to understand the output of intrusion detection systems. And more recently in Konstanz, I've been working with a group of biochemists, helping them deal with data sets coming from high throughput screening experiments. So, unfortunately, I don't have enough time to show all these things together, so I will have to focus on something. I will focus on clutter reduction, high-dimensional data, evaluation, and I don't have time to show more applications, but if you have any questions afterwards, I will be very happy to show you demos, videos, or discuss what we did, okay? Okay, so let's start with clutter reduction. This is part of the research I've been doing during my PhD in Rome. So the main question of this work is, what is clutter and how can we model it first? And once we have done that, how can we reduce clutter and keep some level of accuracy? Of course, these two questions are related one to another. So in order to address this question, we started with a simple model. We started by analyzing scatter plots, which is basically two axes, and every point is every pixel is one point in the database, and started reasoning about the fact that one of the biggest problems, one of the biggest sources of clutter in this kind of visualizations is the fact that for any given data point, it can happen that as the database size increases, you have a lot of data points that are falling on the same pixel in the same position on the screen. So we started analyzing these kind of visualizations in terms of dividing the visualization in bins and creating a whole bunch of metrics according to what we can see within each bin, and counting, for instance, how many data points we have here compared to how many pixels are turned on, and so on. So, for instance, one thing that we have been doing is to work on these two specific kind of densities that we call data densities and represented density, which basically means what we have in the data space and what we have in the image space, and then try to do things in the image space in a way to recover what we see in the data space. So, just a simple toy example I have here. It means that, for instance, if we have, this is the data density, the number of data points that fall in these two bins. If we go in the image space, the difference is preserved. But if we take these two bins in the image space, the difference is not preserved. So we have a whole bunch of metrics that basically work on top of this idea, trying to compare the image space to the data space and trying to preserve the differences in terms of density. So we came up with all these metrics, and I want to focus on these two. So we had one that is what was called lost data densities ratio and perceptually lost data densities ratio. The first one means basically we take every pair of density of bins on the screen, and we compare the difference in the data space and see whether this difference is preserved in the image space. And then we adjusted this measure by running some user studies, trying to understand how users perceive the level of density in the visualization, and actually trying to take into account how these are perceived. Okay? And then, of course, we try to come up with techniques to reduce the amount of elements, of objects on the screen. And we had, at the beginning, something that is called interactive sampling, then automatic uniform sampling, and finally, automatic non-uniform sampling. So the idea is always the same, trying to reduce the amount of information on the screen with sampling, but doing it in an intelligent way. So initially, we just used interactive sampling, giving the user the opportunity to choose the level of sampling, but this doesn't work with large data sets. So then we moved to a uniform sampling that is automatic, but then we noticed that the problem there is that it doesn't matter how clever your algorithm is. Either you are oversampling in one region that is too dense, or you are undersampling in another region that is not dense at all. So we came up with an automatic non-uniform sampling algorithm that tries to preserve as much as possible these density differences that I've just shown to you in the previous slide. And we have an algorithm. This is the sketch of the algorithm. Basically, in the first step, we create a mapping between what I call the data densities into the represented densities in a way that we have a more uniform distribution of these densities. And then we have the second step that is actually realizing these target densities. Because the problem is, how much do I have to sample? Since now every bin has to be sampled with a different amount of sampling, we have to know how much we have to sample to reach the target density in the visualization space. So we have predictive functions that basically tells you how much sampling you need in order to achieve a certain amount of visual density. And these are examples of images that we could automatically adjust and enhance. So for instance, as I said, we started with simple scatter plots, and then we moved to other kind of visualizations like this one that is called star coordinates. And as you can see, you go from a very flattered view to seeing better some shapes in the visualization. And then we move to more complicated visualizations like parallel coordinates by adapting some of the algorithms that we have here to these kind of representations. Okay. As I said, so basically this first part of my work deals with large numbers of records, if you think in terms of a table. Now the orthogonal problem is how do we visualize data which has too many data columns, if this is the table. Of course here we have a whole set of problems again, because the number of visual features that we have available to represent multidimensional data is very limited, so it's not clear how to do that. I give you a simple example. If we want to visualize data with a scatter plot matrix, this is the result we get with 4 dimensions, which is still quite okay. This is the result we get with 20 dimensions, which is kind of okay. And this is with 100 dimensions, right? We cannot see anything here. And 100 dimensions is not that rare, right? I mean, it's quite common today. How do we visualize this data? So one idea is the idea of using quality measures to automatically find interesting projections in high-dimensional data. So what do I mean here with interesting projections? So here we started, again, with something simple. We have simple scatter plots with pair of coordinates taken from the original data set. So it's not dimensional reduction. So every view here doesn't represent a whole bunch of dimensions. It's only a pair of dimensions, okay? But again, as I've shown to you here, even just selecting a pair of dimensions, you might have a very big problem here, right? So we take all the possible pairs of dimensions and we create all the possible scatter plots over there. And of course the list is very, very long. So now you cannot give the whole list to the user. So what we want to do is to capture the interesting scatter plots there, the interesting projections. So the question is, how can we measure the interestedness of a projection first? And the second is, does this correlate with human perception? So we started analyzing a number, developing some measures, analyzing some other measures that we could find in literature. So the first one, so we had class consistency, histogram density, 1D, 2D, and class density. This is one of my PhD students who did this work here. And I will show you one of these measures just to let you understand what I'm talking about. So the idea here is to, if we have classified data, trying to find those projections in which we can clearly see the classes separated in the projection. They do not overlap too much, okay? And one of the measures that we use is called class density measure, where we basically do these steps. We start from the initial representation, we create as many images as the number of classes, then we move to we translate this into a density field in order to go into the image space. And now we take, for every single pixel on the screen, we have a density function that represents what's the density in the neighborhood of this pixel. And now we compare for for every pixel, we take all the possible pairs and see what's the difference in density. And of course, the higher this difference, the better the measure. Okay, so we sum it up and we have a final measure. This is one of the measures that we analyzed. Okay, just to let you get the feeling of how it works. We also have measures that work with unclassified data. Then we ran a user study, and the idea here was, so okay, if we can use an algorithm that does that, does this algorithm behave the same way a human would behave if this person would have the opportunity to look into all these projections? So we created a small user study taking the wine data set from the UCI database with 178 samples, 13 attributes, and 3 classes. We had 18 undergraduate students participating, and exactly a whole bunch of scatter plots, of course not too large because otherwise the experiment would be too complicated. And we asked them select the projections that are suited to classify the 3 types of wine. Okay? And of course what you expect is that these people are selecting projections like this one, where the colors are well separated and not mixed. So if you take this one, they are all mixed. Okay? So these are good projections and these are bad projections. So we compared these four measures, and this is the correlation that we got from the measures. So here is the user classification versus the score that the measures gives to the scatter plot, and every single point is a scatter plot. So as you can see, they correlate quite a lot, but they correlate with different values according to which measure is used. So histogram 2D and class consistency work much better than the others. And one outcome of this study is that we noticed that the problem here is that the reason why these measures don't work too well in some cases is that either they take into account the amount of overlap or the density. But in order to get better results, we would have to take into account these 2 things at the same time. And this is actually what we would like to do in one of our next steps. Another thing that we are currently doing, actually during the last few days I had some people in Konstanz working on that. I feel guilty that I couldn't help too much then. So the idea now is trying to do a similar thing, but instead of using pair of axes, now we take every possible combination of dimensions. Of course, if you think about it, taking all the possible combinations of dimensions is a huge space. So what we do here is first to run an algorithm that reduces this space, and then we create a visualization that helps people detecting interesting subspaces and compare them. One interesting aspect of this work is that the idea of finding what is called alternative clusterings. It means that in different subspaces you find different clusterings which actually capture different concepts in the data. Okay, this concludes my technical part, and then I will move to evaluation. Do you have any questions so far? Is it clear? Yeah, please.
I don't know, I can exactly, yeah, but have you considered more like traditional statistical measures like entropy, density estimation to do the same sort of thing? Is there
In the quality measures?
Yeah, for instance.
We have entropy actually. We have another measure with entropy. I didn't show it, but we have another, the histogram 1D and 2D actually creates histograms on top of these scatter plots, and then it measures entropy there. I can explain to you offline. Yeah, but yes, we have entropy. So evaluation is a big topic in visual analytics. The question is, how do we evaluate visual analytics? And these are some of the questions that I always get. When is a visual analytics solution better than another? Under what circumstances? And why? Or how can we systematically explore a solution in order to check whether it works or not? And I think this is a very important question. And I personally think that without a solid and systematic evaluation visual analytic strategy, visual analytics basically is like playing darts, because if we don't have a way to say this is better than this, then anybody can come up with a solution, because it's not that hard to take some data and create a visualization out of it. But creating an optimal visualization is really hard. So I think that I think we really need to have these methodologies, otherwise it's very hard to be taken seriously in some of these areas. But at the same time, evaluating visual analytics is really hard. Why? So one reason is that it's really, really hard to be evaluated automatically because there is a human in the loop. So you have in the evaluation to take into account the human. And also the metrics are not always well defined. The second point is that visualizations are very complex artifacts. They are made out of visual representation and interaction. It's not only the representation itself. Plus, the performance doesn't depend only on that. It depends on the data, on the tasks, on the users, the environment, a whole bunch of things. Finally, the tasks are not always well defined. It's not always clear it's very hard to translate visual analytics task into try to do that. Normally, you want to discover something with this kind of tools. So you want to, in a way, to capture the aha moments there. You want to discover. So, in order to address this problem, I starting from 2006, a workshop that is called the BELIEF workshop, which stands for Beyond Time and Error, Evaluation for Information Visualization. And I did that with a whole bunch of guys during these years, with Ivy Lam from Google, Adam Keller from IBM, Catherine Pleasant from University of Maryland, and Giuseppe Santucci, who was my PhD advisor. And we created this workshop series where we discuss these methodologies, and we came up with a lot of new methodologies which are really, really interesting and promising. And we also edited a special issue in the Information Visualization Journal with a whole bunch of new methodologies. I think if you are interested, this issue is really interesting. Of course, I've not only organized events, I'm also trying myself to come up with evaluation methodologies and strategies. And this is something I want to show you because it's very recent. This is going to be published at the next Eurovis. And it's interesting for me because it's the first time I try to use a methodology that is a little bit innovative in a way that we try to go beyond the idea of assigning tasks to users and compare visualizations in terms of time and error. This is basically the idea. So what do we have here? Again, this comes from the same project I've shown at the beginning. We have flow maps, stuff that is flowing from one region to another, and it's changing in time. So the problem here is that two obvious solutions to this problem is to use either animation or small multiple. But the idea in small multiple is that you are transforming time into space by adding for each year one representation, and now you can see the whole development of this flow map in time. Okay? So there are advantages and disadvantages for both cases. And what we wanted to do, instead of assigning specific tasks, we wanted to see, so the question in our mind was, what if we try to collect all the findings that people can extract by using these representations, and then once we do that, can we see differences in the kind of findings that people find there? So one challenge of this methodology is that we have a completely open-ended protocol. So what happens is that the participants are asked to search for findings, that they collect findings in form of notes. So the tool was instrumented in a way that people could actually write down notes about their findings. And then they start with one interface and then they move to the other interface. And of course this is counterbalanced. If you start with A, you go to B. If you start with B, you go to A. And then there is a quite complex process done by the researcher which manually have to code the findings using a technique that is called axial coding, which means basically I have a whole list of these insights or findings, and now I have to find the categories to categorize them. So the idea is that the process itself helps you coming up with these categories. And then what you want to do is to search for differences in these categories. Plus, of course, what we did was to have video recording and interaction logs of what these people did with these interfaces. So this is one of the results that we got from the experiment. So basically, we came up with two main categories to categorize the findings. One is temporal scope and the other is geoscope. temporal scope basically means, is the finding something that is related to one specific year or a set of years? For instance, this flow happens between these two countries in 1997. Or another finding with a larger temporal scope would be between 2000 and 2010, this thing has happened, okay? Of course, we have the equivalent in the geospace. So does this happen in one region or in a whole set of regions? And what is interesting here is that, so let's take, for instance, the temporal scope. So these are the people who started with animation and then moved to small multiples. And these are those that start with small multiples and then go to animation. And you can see that pretty consistently you have exactly the same shift when they move from one representation to the other, which is interesting because it means that regardless the order, there is always the same shift in the kind of findings that they find, okay? And one consequence of that is that basically animation and small multiple promote different kinds of findings. And a consequence of that is, if I want to build a new system that has this problem, what do I want to promote? And if I want to promote both, how do I integrate both techniques? So these are some of the questions that came out of this study. Okay, this concludes my work, and I will say a few words about my future plans. Do you have more questions here? Okay. Okay, so I have a 50,000 feet goal, very, very high level goal, which is basically helping to build the science of visual analytics. More precisely, what do I mean? I mean, understand what works, when, and possibly, hopefully, why, which is really hard. Learn how to couple automatic and interactive methods effectively. Make visualization more scalable. I love this quote from Ben Schneiderman. He says, squeeze a billion items into a million pixels, which I think it pretty much explains what we need to do here. And then create, as I said, I would really love to create systematic, robust, and defendable evaluation methods to explain, to be able to say, this is better than this, and this is the reason why it is better. Of course, I don't want to do this only in theory. I want to do it in the context of solving problems for real people with real data. There are two specific things that I really, really want to do, and I'm actually kind of doing right now. The first one is to do what I call visual data mining. The idea is, I think that there is a huge space here for taking data mining techniques and coupling these techniques with visualization in a way that the two things can play together in a better way. So, for instance, I want to use visualization to interpret mining output, which I'm actually already doing, make sense of complex parameterization, because many mining algorithms have very complex parameters and it's not clear how to set them, and also ideally enable a mixed initiative model building where the idea is that visualization plays the role of seeing the intermediary states of an algorithm. I started a project in Germany where I got this grant from the German Science Foundation called SCIIva, which stands for Steerable Subspace Clustering for Visual Analytics, together with Professor Seiler in Aachen, who is one of the leaders in data mining in terms of analyzing these subspace clustering algorithms. The second thing, in terms of evaluation, I would really, really like to go into the idea of using human logging to evaluate visualization. There are a whole bunch of technologies that can help us to have a more direct sensing of what people do when they use visualization. And two very promising technologies are eye tracking and brain-computer interfaces, and I would really, really like to go into this direction. One last thing before I end, I have only a couple of slides more. Of course, I also care a lot about public outreach, and I think it's really, really important to bridge what I call the practitioners and academics divide. So a couple of years ago, I think 1.5 years ago, more or less, I started thinking, I see so many beautiful visualizations on the web, but at the same time, I see this problem. There are many people who are not academics who generate visualizations, and in many cases reinvent the wheel because they don't know what we have been doing in this field for the last 20 years. On the other side, I also have the feeling sometimes that people working in academia don't realize that there are designers or engineers in the real world who create very remarkable visualization designs. So I thought I have to find a way to let these people talk. So I created a blog that is called Fell in Love with Data, and with the intent of talking about visualization in a way that I could explain to people what we do in academia and trying to create this bridge. And I think this is happening in a way. So I get emails from professors, like, I don't know, this is one from Tamara Manzner saying something like, I don't remember, bridging between academics and the rest of the world is a very useful thing to do. You manage it with an inimitable combination of verve and thoughtfulness. That was the best one I received so far. But also George Greenstein or Ben Schneiderman, they say, yeah, fantastic, go on, you have to do it, keep doing it. And at the same time, I have people from industry who are inviting me to talk about visualization. So there was this very nice event called Visualizing Europe, organized by GE. They create terrible visualizations. And it was...
Let them know.
It's important. In a way, it's important, right? And we cannot just say, oh, that's bad, right? They are trying to do their best, I think. It's not bad. I was invited by an agency in Canada last year. I'm going to talk in this Big Data World Europe, which is an industrial conference. So it's kind of happening, and I think it's important. So I started my talk saying, building the science of analytical reasoning facilitated by visual interfaces together. I think together is important. I think there are many, many ways to build visual analytics together. For instance, here at Utah, I gave a look toward the Department of Computing. This is the list that you have on your web page. And I think that either visual analytics can help you, or you can help visual analytics, or both. So I think this is, I mean, I might be wrong, but if I take every single instance here, I am sure that either visual analytics can help, or you can help visual analytics. This concludes my talk. I have a few acknowledgements. Of course, my work is supported by many, many people and students, and they are really fantastic people. Andrada Datu is the person behind this high-dimensional data analysis, and Rich Strobel. He did all this stuff with biochemists that unfortunately I couldn't show here. Ilya Boyandin is the person behind these flow maps. Miros Kristajic is the person behind the visualization for streaming data, which I couldn't show here. And of course, my mentor, Professor Daniel Kain, who helped me really a lot so far. Professor Oliver Duysen, again, he is also in Konstanz, and he was in charge of this biochemical project. Denis Lalande was my supervisor in Switzerland, and Professor Santucci, my supervisor in Rome. And this is the whole bunch of people we have in the visualization group in Konstanz, and it's really great to work with them. This concludes my talk. Thanks a lot. And
any additional questions? Ross?
Yes.
Hi.
Hi.
Nice talk.
Thanks.
In some of this evaluation work, there's a whole, in the last couple of years I've been aware of a whole set of work over in psychology, perceptual psychology and cognition that actually is applied work on sort of visualization and understanding things like this. And of course, these folks have a lot of experience in setting up studies and making sure, that they're, that the results can be interpretable and so forth. Do you work with folks like that in the evaluation studies, or how does that work?
I never worked with cognitive science experts. I know some of them. Brian Fisher, I think you know Brian Fisher. No, I've never collaborated with them. I've collaborated with people who are expert in evaluation in general, like HCI people.
Right, okay, right. Similar, yeah.
Especially this belief workshop normally is very well attended by people who come from HCI. Actually, I didn't say by it was organized twice at the CHI conference, the main conference in human-computer interaction. And basically in this workshop we have almost always people who are InfoVis people but have a sort of HCI branch in their research. Okay? Yeah, so I've been collaborating and discussing with them quite a lot. But I have to confess that I've been doing evaluation only recently. First of all, because I realized that it's really important. And second, because my initial experience with doing evaluation the way the others do is really bad. It's really, really hard. And the kind of answers that we get from standard controlled experiments are so narrow that I'm frustrated myself, and I want to do better. Please.
So at the beginning you had said that your view of visual analytics was that if it could be, I think your golden rule was that if it could be done automatically, it's not really visual analytics. But do you think that the systematizing of visual analytics is going to slowly move us towards it being automatic? So where do you see the breakpoint being where, even though we can systematize it, that there will always be a human in the loop? If you think that's going to
That's really interesting. I think there are two kinds of
and
problems.
the alternative is you got a 5-year plan. You systematize it all. And visual analytics is done. Remove it all over here.
I really like this question. I think there are two kinds of problems. There are problems that, in my view, will always need a human in the loop. But there are some other problems, and I have seen it quite sometimes, where the problem there is, I think, so there is an analyst there who said, I think I could do it automatically, but I don't know yet how to do it automatically. And I use visualization as a source of inspiration to understand how I could do it automatically. There is a very nice paper published, I think a couple of years ago at the CHI conference, by a bunch of people, I think from Microsoft, who had these researchers who want to build classifiers from ensemble classifiers. So ensemble classifier, the idea is that you want to create a strong classifier by training several classifiers at the same time and then taking the best of them, okay? So they couldn't find the best classifier even with ensemble methods. So they have a very nice visualization system which helps them selecting instances to actually categorize and say, for this kind of instances, I want to use this and this classifier, and for these other kinds of instances, I want to use this other classifier. By using visualization, they actually came up with many more ideas to how to do it automatically, and I think actually they did it. So I think we have these two kinds of problems. Problems that we always need humans in the loop, and problems that basically are a sort of entry point to understand how to do it automatically.
And what would be representatives of the first two problems for which you think we always need to do that?
I don't know. I've been working with biologists, and these are people who, it's really impressive. I mean, at least the people I'm working with, they run an experiment, and it takes a few hours to spit 100,000 data points, 100,000 molecules with very long binary vectors. They have no idea how to do that. So now they have to find, I don't want to be too technical, but basically what they want to find is molecules that react, but at the same time have other properties, but at the same time, if you have these properties, they don't react very well. So it's not just a matter of finding the molecule that reacts best. So now they want to see which structure, when the structure changes, how the activity changes. You have to see that with your eyes, because you have to apply your domain knowledge and actually get an understanding of what is happening there. There's no algorithm that can actually tell you that's the best one, because in the process, you need the domain knowledge. So I think it's really, really hard. I mean, I might be wrong, but I don't think I am wrong. And problems like this that are everywhere. Even these ornithologists, I've not been working with them, but I've seen them working with my colleague, Florian Mansmann. They see the visualization and say, oh, yeah, finally, I can see it now. I mean, how do you analyze birds that are migrating from one country to another? I don't know. I might be wrong, I mean, but did I answer to your question? Okay.
Other questions?
Yes.
So one of the first things you talked about was when you have this huge amount of data and you have this clutter you're trying to, you're trying to eliminate some parts of the data from the clutter
Yeah.
by doing some special sampling.
Yeah.
I didn't quite get exactly how you did that sampling, how you ensured that you had the right, how you were sure you had the right representation.
Okay.
Could you just say another couple sentences about that?
Absolutely. Yeah. So the way we do it there is, so what we do is, so the goal is this. We see all the possible differences of densities in the data space by binning the space. And now the goal of the algorithm, even if it introduces some distortion, is to keep as many density differences as possible. That's the goal of the algorithm. So now the way this algorithm works is that it tries to create a new mapping between the data densities and the represented densities. Okay? So now what the algorithm tries to do is to apply a more finer grain of differences in densities where there are more density differences in the visualization,
okay,
and use a more coarse sampling in the areas where there are few differences. Okay, that's the
so is this thing you're doing where you had the sparse grid, the coarse grid?
Yeah.
And there, did you have any problems when you were discretizing the data based on the grids that your representatives of the density were fixed according to that grid?
You mean,
that grid?
do you mean if the grid has an influence in the result?
Correct.
Yeah, absolutely. Actually, what we did a number of experiments, and we discovered, so one thing that maybe I didn't explain very well in the talk is that our prediction function that tells you how much you have to sample in every bin works on the assumption that you have random data projected in the bins. So our work is...
So it's assuming there are no trends within a bin.
Yeah, within a bin there's no trends. And in order to have this assumption valid, the bin has to be small enough. So our experiments basically led us to show that we have to have bins that are small enough to keep these assumptions somewhat true.
Okay.
Other questions? Okay, let's thank Enrico for that. Join us again here on Wednesday for part 2.
I have more stuff to show.